Okay, welcome back. This is the second day of learning about linear algebra. Things are going to feel a little bit different today than they were the last day. A lot of the things should have felt familiar the last time. We're going to see some new notations here, and actually even a couple new definitions that I don't think you would have run into before. So here we're going to be working on section 2.3. The section is called Norms on Finite Dimensional Vector Spaces. And particularly this word norm, you might have heard it before with reference to like absolute value. You might have heard it with reference to the complex numbers, which I already mentioned. But all of a sudden now we're expanding these norms to vector spaces. So placing norms on vectors. You probably heard about norms of vectors before, but we're actually going to be placing norms on matrices as well. So, and there's a little bit broader definition that we can use for norms. So first of all, I'm going to introduce this new notation. This notation is for an inner product. And the reason why I use this notation instead of the dot product, you've probably heard of your standard dot product referred to as an inner product before. That's just because I am generalizing the dot product. So this word inner product that we use can mean a lot of things in the outside of the context of just like finite dimensional linear algebra. So dot products are really restricted to meaning finite dimensional linear algebra cases. Inner products are otherwise. And we're really going to be heading into that universe of other vector spaces that aren't necessarily finite dimensional in this class. So that's why we're going to talk about the inner product right now, and I'm going to introduce this notation. These are brackets. They're angled brackets, not quite the same as like less than or greater than, right? You can see they're a bit taller and broader than those. But these are angled brackets, and we're going to refer to inner products with these angled brackets from now on. But for now, you can just think about them as, yes, they are the dot product. I'm defining them the same in finite dimensions, and because of that, how do you compute a dot product of two vectors? Well, you just take their entries, the jth entry of each vector, the jth entry of x times the jth entry of y, and then you take the sum all the way up, right? Turns out in complex numbers, right? So if we're sticking ourselves in real numbers, that's perfectly fine. If we move to complex numbers, turns out we want the second entry in our inner product to gain a conjugate. So that's something that maybe you haven't thought of before. There are really good reasons for doing this, and we'll see why just in a little bit. But we really want the second entry of an inner product to be given a complex conjugate, okay? And then we're going to sum over the entries multiplied together the same way we always would. So let's take an example. This is an example without complex numbers, because a lot of the times in this course we won't be using complex numbers until we have to. But let's look at x being the vector -1, 0, 1. I put a transpose there so you know that this is in fact a column vector. And y is the vector 1, 2, 1 to the transposed. And then we can take their dot product. It should just be -1 times 1, 0 times 2, 1 times 1. And that's exactly what we see. And we add those together, we get 0. It turns out they're orthogonal in this case, if you remember what that definition was. But there's an example of taking a dot product. Now we're starting to get into some new notations. Okay, so the two norm, right? Now I'm giving myself a different name on norm, and I'm using two vertical strokes to talk about the norm. So generically in math, we actually do use two strokes to define a norm, or describe, I should say describes a norm. And this is generically. Whereas the single bar often describes magnitude. Okay, and I realize that in many cases they should be interpreted the same way, but we really just want to start saying that, norms, there may be a way for us to define these where they're not necessarily magnitudes. And that's why it's kind of important to think about using the double strokes norm instead of a single stroke norm. And then in fact I've actually given a subscript 2 here, and you might be wondering why I gave a subscript 2 there. Well, it's because subscript 2 corresponds to Euclidean norm, since right, the norm, or the magnitude squared on x as a vector, is the sum of xj squared. J equals 1 to d. Okay, so the 2 right here, the 2 right there, and the 2 right there are all the same 2. It turns out that there's perfectly valid norms if I replace those 2's with another positive number greater than 1. Greater than or equal to 1. So actually if I put magnitude signs there, and then I make the power greater than or equal to 1, then actually it defines a norm in the sense of any norm. But anyway, I'm getting ahead of myself. It doesn't really matter for this course because most people like the 2 norms the best, so we're going to use the 2 norm in this course. We just calculate that by taking the inner product of x with itself and taking it to the 1/2 power. This is why it would matter that in complex cases, this definition describes why in complex cases we take xj, yj bar, and then we sum. Right, because we want, if I'm taking the inner product of x with itself, then I'm actually taking the product of x with its conjugate, which would give me the norm of x. It would give me the complex magnitude of each of those entries. So that's really one of the reasons why we like placing the complex conjugate on the second entry in the inner product. Well, anyway, so that's our classic. This is the classic Euclidean norm. I don't want this notation to scare any of you. Standard Euclidean magnitude. New name. New notation. Just be aware that it could possibly change. A lot of mathematicians do change it. All right, let's look at the example with the same x that we had before. So it's this column vector, except with the transpose there, -1, 0, 1. I'm just going to take the inner product of that vector with itself. So I'm going to square -1, square 0, square 1, add them together, take it to the 1/2 power. I get the square root of 2 is the norm of that vector. And see, now we've moved to why it's actually kind of cool why we have norms, is that we can define norms on matrices. And this is definitely not something you've probably encountered before. So defining the norm on a matrix is a little bit tricky. It's got a kind of a funky notation here. We're going to take the maximum value of all vectors with norm 1, and we're going to take the maximum value of image under the matrix. Okay, so how can we think about that conceptually? Let's conceive of this a little bit. This is the greatest distance from the origin, the image of the unit sphere takes under M. Okay, so M, right, maybe I'll draw this over here. Got my unit sphere here. Really good drawer. Oh yeah, so there's my unit sphere. And M comes along. And remember, M shrinks and stretches in higher dimensions, right? So M comes along. And I know M's continuous, so this still looks like some sort of weird continuous shape, because it looks like a fish of what I decided. Okay, it does something like that. That's what M does to the unit sphere. And you'll notice that there's one particular place over here, right over there, actually probably right up here. That distance got mapped to there from somewhere on the unit sphere. Maybe that point was right here or something. Maybe that point came all the way over there. Whatever that distance is, that's the 2 norm of M. So it really just gives us a way of saying, okay, what is the most that this matrix can stretch things, right? Because since it's linear, if it stretches the unit sphere so far, it's going to stretch every other vector at most that far as well. So that's what it's really saying as well. You can think about it the other way. This is the most M can stretch a vector by, right, in multiplication. So the most it can possibly stretch a vector by is its 2 norm. All right, so I've got a little example here. Define a matrix here. Turns out that the 2 norm of this matrix, not terribly intuitive, that this matrix, the most it could possibly stretch something, is 2 plus root 3, all of that square root. So it's a little bit not intuitive, and I'm not going to show you how right now. This is exactly exercise 2.4 at the end of the chapter. So turns out, you'll find out when you get there, you can use Lagrange multipliers to solve this for you. So you might ask me why we care about norms in an abstract setting. What do we care about magnitudes? And the answer is that actually norms tell us about convergence. or they let us talk about limits. You kind of think about limits and convergence the same. So you can embed the matrices into this vector space of matrices, and then you talk about, okay, the norm's absolute distance to the origin, so then if you're taking the norm of a difference of two elements of a vector space, and that norm tends to 0 as n goes to infinity, that means that they have to get infinitely close together. Okay, suppose I have x, this says xn gets infinitely close to x in an arbitrary normed space. Normed space. That's what that's saying. You'll have to excuse my spelling on normed. So it's just saying that, you know, the reason why we kind of care about this for this course at least is that, you know, we can embed things into, you can make vector spaces and norm spaces pretty broad, and knowing about norms tells us about the convergence of vectors in those spaces. So that's really nice. So turns out that we're going to care about a sequence of matrices converging to another matrix. And this jumps all the way back to this idea that we want to define this. Want to define e to the tm, an exponential of a matrix. And if the power series converges, then we're good to go. If it doesn't, then we're not. And it's really nice to know that power series converge, and the reason we can do that is because of norms. That's why we care. And that's what that section's all about. And now we'll move on to the next section, which is called spectrum of a matrix. And this might be a little bit of a scary word, but really, this is our fancy mathematician's word for eigenvalues. So just think about this section as the eigenvalues of a matrix, but we're going to give it a new name, spectrum, and we're going to sound like really cool mathematicians. Okay. I've got a little intro there about motivating eigenvectors. You can read that if you want to. But let's just recall what eigenvector eigenvalue pairs are. They're described right here. By that definition, mx equals lambda x is the definition of an eigenvalue eigenvector pair. So we define the pair x lambda, where x is the eigenvector and lambda is the eigenvalue. Okay, but the real question is, how do you find these, right? Defining it's one thing, finding them is the other. So I'll say finding these is perhaps the most important part of linear algebra, but honestly, a lot of other math. Okay, we're gonna see in this semester that a generalization of this equation is super important. So a lot of what we try to do in math is finding these. So it's always nice to know when we can find them. So let's define the spectrum. Okay, suppose that we have these. We're going to define the spectrum as spectrum of a matrix is the set. Okay, this is a mathematical object set. If you had intro to proofs, you know what these are. So the mathematical object of a set of eigenvalues of m. Okay, so I've defined it then. We're going to use a lowercase sigma to define spectrum, sigma for S, and spectrum of the matrix M is the collection of eigenvalues in C such that there's actually an eigenvalue eigenvector pair for M. And this is the whole reason why we needed complex analysis. Which was chapter 1. Right, so the whole reason why I introduced complex analysis in chapter 1 is so that the spectrum actually makes sense. I already talked about it back then, because if you have a real matrix, you're not guaranteed a real spectrum, but you are always guaranteed a complex spectrum for a complex matrix. Let's talk about finding these. And a lot of you have probably noticed that that is a much easier equation to solve than that. And all I've done is I've subtracted lambda x from both sides. And we know that the bottom equation here is equivalent. Since it's equal to 0, that means that the null space is non-empty, right? If that has a solution, hence null space of m minus lambda is non-empty. And we know exactly when the null space is non-empty because that means it's not invertible. And the proposition I told you that you needed to remember is that non-invertibility, it's the contrapositive of the statement that I had you memorize. Non-invertibility is equivalent to the determinant being 0. So that's the most important. That's why it's really, really important. We have all these nice statements. Non-invertibility is equal to determinant 0. Well, non-invertibility is the same thing as the null space is non-empty. And boom, that's how we find eigenvalues. Here's our following theorem. The spectrum of the matrix is precisely the values in the complex numbers for which the determinant of the matrix minus lambda times the identity is 0. And what's beautiful about this is that this expression is always a d-degree polynomial in lambda. So we say that we can find the spectrum exactly by solving a d-degree polynomial in lambda equal to 0. And that immediately gives us a beautiful corollary. It tells us that no matter what matrix we have, the spectrum, this is the empty set, by the way, the spectrum is non-empty. The empty set is the set with no elements inside of it. So this says that the spectrum, there's always at least one lambda. I'll translate that here. So this is equivalently always at least one lambda in the spectrum. There's always at least one lambda in the spectrum. That's so nice to know. And how do we actually know that? Well, we have to jump back to the complex analysis chapter. We have the fundamental theorem of algebra that says that every polynomial of degree d has at least one root. In fact, it has d roots when you count multiplicity, but you have at least one by the fundamental theorem of algebra. So we always know that we can find at least one eigenvalue. That's fantastic. So let's look at a nice example here. So given a matrix, this is the one that I was looking at earlier, can I find the spectrum and the associated eigenvectors? Well, let's work it through. Let's work this through. The first thing I need to do to find the spectrum, recall spectrum means collection of eigenvalues, is calculate the determinant m minus lambda id. This is going to be a polynomial in lambda. I do that by subtracting lambda id from m, and I recover that matrix. I take its determinant, it's the diagonal minus the off diagonals, and I recover exactly 1 minus lambda times negative 1 minus lambda minus 0, and simplifying that a bit gives me the polynomial lambda minus 1 times lambda plus 1. When is lambda minus 1 times lambda plus 1 equal to 0? Well, it must be exactly when lambda is 1 and lambda is negative 1. Therefore, we've found the spectrum. So the spectrum is exactly the roots of the polynomial in lambda of determinant m minus lambda id. That's always what we want to think every time something asks us to find the spectrum. Finding eigenvectors is a little bit trickier, but you've probably done this before. All we have to do for this is calculate the actual matrix m minus lambda id for one of the lambdas we've already found. So we suppose lambda equals 1. We know that's an eigenvalue. We plug that into m minus lambda id and act it on a vector x. We know that this should be equal to 0. Here's my vector 0 if x is an eigenvalue vector. If x is an eigenvector, then this must be equal to 0. Well, that helps us find x, the eigenvector, because we act that matrix on x1, x2, set it equal to 0, and we'll notice that this is x1 times 0 plus 2x2 equals 0, or x1 times 0 minus 2x2 equals 0. Either way, it gives us the equation 2x2 equals 0, or rather, x2 equals 0. Notably, that means x1 is free. When you're finding eigenvalues, one of them will always be free. Or eigenvectors. So when you find eigenvec, one of the entries in the eigenvector will remain free. Okay, so in this case, x1 is the one that's remained free, which means, and x2 has been set to 0, so we keep x1 free, we set x2 to 0. If I want to, I can pull x1 out of that vector. And I know that this is an eigenvalue, or eigenvector for any non-zero x1. For example, make my life easy, let x1 be equal to 1 gives me the eigenvector that I'm probably looking for. And I'm going to notate with a subscript. My subscript says associated to lambda equals 1. So I'm using the subscript to define, okay, what is the eigenvalue that this is associated to. I can go through the same process with my other eigenvalue being lambda equals -1. And if I do the same process there, I recover this matrix on x1, x2, which must be 0, 0. And this matrix gives me the equation 2x1 plus 2x2 is 0, which I can solve for x1 being equal to -x2. Now, notably, that's just a relationship between the variables, but if I want to do that, I can rearrange my vector, this vector right here. If I take that vector along with these together, gives this vector, right? So what I've done is I've replaced x1 with a -x2. And once I do that, if I want to factor out an x2, I certainly can. And this is going to be an eigenvector for any non-zero x2. Well, making my life easy and letting x2 be equal to 1 gives me specifically the eigenvector -1, 1. So those are the eigenvectors associated to the eigenvalues. That's all I have. I'll see you in class.